Our next talk is going to come from Ben Feist, and Ben is bringing us horizontally integrated informatics to support science operations in human spaceflight. Take it away, Ben.
Great. Is everybody able to hear me, and can you see my slides?
We can. Thanks.
Excellent. Thank you. So really, I'm going to talk today about how managing our mission data can enable science support operations when we go on future missions. That's essentially what this is all about. First, to just describe what the problem is. Really, this is about PDS, is what we use for our remote sensing and our current robotic missions. But how can we make data useful during the mission when addressing this problem? Science and engineering data are equally valuable for human exploration missions, especially when it's real time. So rather than just thinking only as scientific data and does it go into the PDS repository, how can we enable science and operations data to work together? And another way to say this is that good science data management equals better ops situational awareness, and better ops data management equals better mission context for our scientific data. And this is all like for real time, try to merge everything all together for support operations. So the way I'm going to describe this is through these 4 levels of enablement. We currently are aware of level 1, where we have the instrument on the spacecraft and we're gathering the data, and we can write papers and do research on that data that we get. Level 2 is making sure that we save that data for future generations of study on the PDS. And what I'm introducing here today are levels 3 and 4. So level 3 is really the key, which is to horizontally integrate, and I'll explain what that means. Locally compatible data enabling cross-disciplinary context within a mission. And then level 4 is doing level 3, but using open data standards. So you wind up actually having globally compatible data that's across missions able to be used, and I'll show how that's an advantage in a second. So I'm going to explain for the remainder of the talk how these different 3 levels of different efforts relate to these levels, focusing on different outcomes that has happened as our team has worked on different systems in order to integrate these. So the first is the Petrio analog from RISE 1, often called RISE 4, which was level 1 instrument data that we're collecting and storing by each instrument for study. And on RISE 1, we went to Kilbourne Hole, which is a Mars volcanic crater in New Mexico. And there we conducted field geology training. We had remote sensing instruments such as LiDAR, and we had handheld instruments such as laser breakdown induced spectrometer that Kelsey Young is using here in this image. And we were using these things throughout an EVA, and these were all siloed into their respective mission SD cards and things like that of this data all just being pulled together. And it was our job to try to move this data to a level 3 like enablement by tying it all together temporally. And we don't have level 2 because this is not planetary data, so we're not putting this in the PDS, but we wanted to get it to level 3. And the result of being able to do that resulted in this prototype, which was a manual effort to get to level 3 for one of the EVAs, because these instruments aren't designed to do this. So this prototype, you can see a digital terrain model where there's GPS tracks walking through it. And this digital terrain model was generated by Jose Hurtado at UTEP. And you can actually see the drone in the bottom right that's gathering that data on the clock during the EVA. And then we have chest cameras. And you can see here astronaut Butch Wilmore marking waypoints where he wants LIBS and XRF data to be gathered on an ash deposit. And then we store that instrument data in the waypoint that was generated during the EVA. So we're essentially coalescing the siloed data back together into when it occurred during the mission, and creating this ability to kind of play back and walk through and get a way better understanding of what occurred than even you may have had during the real-time event. This prototype is several years old, and it was the very first example of this approach being used on analogs. The next example is at the Neutral Buoyancy Lab, and this is non-scientific data. This is operations data, and it's also stored at level 1 at the NBL, where we have videos, suit telemetry, and audio. And I did a similar effort to try to get angle joint information about the underwater remote manipulator arm, video and telemetry and suit telemetry, and pulled it all together and said, hey, would this be a useful thing if we could get our ops data all organized like this? And then demonstrated using a anomaly event, would this be something useful for actually tracking things that go wrong or are unexpected? What if you had a way to rewind and just go back and do this? Like, how much time would that save in your anomaly investigation? The answer is a lot of time. So this is a manual level 3 again for operations data. And this is a picture of the nearly completed application that is near automated level 3, but it still requires some underlying data to be gathered in a different way. This approach is being applied at Johnson Space Center under a program that the authors of this talk are working on called EMSS. It consists of 3 component applications. The first is Maestro, which is a digital EVA task planning platform that I won't talk about today, but it's basically gathering the EVA tasks that are being planned to be done in a way that can be digitally recorded as to what events occurred when. We have Aegis, which is a GIS application that allows for traverse planning and tracking, similarly gathering information in a digital form. And then Coda, which is an application that I'm going to talk more about today, which is the playback of all this contextually gathered data that's gathered at level 3 natively using those first 2 applications.
2 minutes.
Sure. So the first application, we have ISS mission context, where Coda is being using the level 2 data that's gathered by the ISS mission, and it's gathered, and you can actually go to it at this URL if you are on the NASA network, and you can check it out. But this is Coda in action. Going through an EVA, you can actually see the different downlinks of data that's available. You can see where the ISS was over the Earth at any given time. For any point since 2013, this data is live and available through the Coda application. So here you can see a playback of a moment of an EVA, and you can pick downlink 1 and 2, and you can actually see the photos appear as they come. It's also useful for non-EVA events. Here's the latest Crew Dragon docking. And because you create a system like this just for EVA purposes, you actually wind up enabling all kinds of operations. Coda is also used on field training. This is one of the rock yard tests that we did at JSC. And here's an example of the rock yard further along that same training event, where you can see the simulated lighting conditions that Noah Petro brought up earlier today being very challenging. The future of Coda will be at level 4, where here's a picture of it, where you can think of it, a certain task during EVA with met rate data and task accomplishment statistics, being able to jump immediately to that same task during training at the NBL, so that you can now trace across EVAs and across training events, similar events and similar tasks, and measure those things. For Survey's RISE 2 that's currently underway, we are going to be gathering field data in November at level 2 and inventing pipelines that will get it to an automated level 3. And in 2022, we'll be able to utilize those pipelines to get near real-time mission science support in the field. And guess what we've made along the way as a natural byproduct of getting Coda to level 4? We've made Apollo in real time for all the current and future mission data that will have our instruments and our research data all placed in context of that mission. And when we go back to the moon with Artemis, we'll be enabling ops and science with Artemis in real time. Sorry for going over time, and I'm pleased to take any questions. Thank you for your attention.
Awesome. Thank you, Ben. That's really interesting stuff. I don't see any questions in the chat. So now if anybody does have questions, feel free to put them in the chat, or just speak up, raise your hand, however you feel comfortable.
Mary, it's Darlene. I have a question.
Sure.
Sure, go ahead.
Thank you, Ben. That was so interesting, such super cool work. And I just wanted to find out if you're aware of XGDS that has been in use with the analogs since about 2008. And I think there's lots of beautiful synergies between what you're describing and what that product's doing, as well as OpenMCT, which is flight certified, that's going to be used on the Viper mission, which is incorporating a lot of the learning that the XGDS product that's been deployed underwater, on land, all over the place, has learned over the years in terms of how to synthesize and data and support science decisioning over latency as well as in near real time. So anyways, I don't know if you guys are in touch with them, but I'd be happy to make that connection, because this is great work you guys are doing. I think, especially given that OpenMCT and XGDS are open source, probably lots of great partnerships and discussions to be had. That's
Yes,
it.
for sure. And we were very much aware of those programs. And the slight difference is that XGDS is essentially the repository for the data and the visualization of that data. And I think that's a byproduct of when it was made and what it needed to solve. We are trying to deliberately just be a visualization of data that is stored by other repositories, so that we never want to keep data ourselves, in other words, because we recognize that you don't want to create new places for data to go and be difficult to manage going forward. So we have lots of systems. So another way to put that is for XGDS, we could use that as a source of information to visualize in the way that we are for science support. But yes, we are in touch with those teams, and we are learning as much as we can from all their experience. They're way far ahead of us in many regards with the work that they've done.
Great. Yeah, thanks for that question, Darlene.